Okay, so hi everyone. In this video, we're going to talk about Lewis dot diagrams of covalent compounds. So first of all, I want to talk about the three different types of bonds we can have within covalent compounds. So the first one is a single bond. This is when two electrons are shared, usually one from each atom. This is the longest type of covalent bond, but it's the easiest to break because it's the weakest. So down in that bottom right-hand corner there, I have a single bond shown between hydrogen atoms. So this is one of those diatomic elements. Remember, Honkelbrief, hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. So hydrogen will form a single bond with itself. Next, we have double bonds. So this is when we have 4 electrons that are shared, or 2 from each atom. This is intermediate in both length and strength, 4 types of covalent bonds. And here we have oxygen, or O2, as an example. And then finally, we have triple bonds. So this is when 6 electrons are shared, 3 from each atom. And triple bonds are the shortest type of covalent bond, but they are the strongest. And nitrogen will form a triple bond when bonding with itself. Okay, so let's go ahead. We're going to do a quick demo. Please go ahead. If you have rubber bands at home, it's great to join along, kind of get that actual real-life hands-on example. Otherwise, you can just watch this quick video. Okay, so hi everyone. I have a really quick demo for you to try at home today. And all that you need are 3 rubber bands. And try and get ones that are the same size, but it's not required. If they're a little bit different, that's okay. So this is going to demonstrate for you the difference between single, double, and triple bonds for covalent compounds. So what I want you to do is first take one rubber band and you're going to stretch it over your 2 pointer fingers. And then without hurting yourself, try and stretch out and see how far you can go. Okay, so notice the distance between your fingers and also the amount of resistance that you feel. Now, we're going to go ahead and add a second rubber band. So this is going to represent our double bond. So again, see how far you can stretch, see the amount of resistance you feel. And then finally, the third rubber band for the triple bond. Okay, so notice I'm not stretching as far and there's a lot more resistance. So that is representing the difference between single, double, and triple bonds. Okay, hope this helps. Okay, so I hope you enjoyed that chance to kind of get hands-on. But let's go ahead and now fill out this table thinking about the length and the strength of those bonds. Well, when I had the single bond, or just one rubber band, it was the longest I could stretch, so that is the longest. When I had the double bond, I couldn't go quite as far, so that was kind of in the middle. And then the triple bond, that one was the hardest to stretch out, so that was the shortest. Now for strength. Single bonds, those are the weakest because they're very easy to stretch apart. Double bonds, they're again in that middle zone. And then the triple bonds, those are the strongest or the hardest to stretch apart. Okay, so that's comparing those 3 types of covalent bonds. So before we get started with Lewis dot diagrams, again, 4 vocabulary terms, but they both mean the same thing. So bonding pair or unshared pair, either term can be used. This is a pair of valence electrons that are shared to create a covalent bond. And when we draw our Lewis dot diagrams, we represent these types of electrons using a line. And then the other term is either lone pair or unshared pair. So this is a pair of valence electrons that are not shared between the 2 atoms. And this is represented by a pair of dots. Okay, so actually let's work now on drawing those Lewis dot diagrams. So the first thing we need to do is determine the total number of valence electrons in the compound. So we're going to think about each element we have, how many of that element we have, and then the number of valence electrons that each element has. And we'll go through examples with that. The next thing is we need to figure out where we're going to place the atoms. So since we're usually going to have more than 2 if we have a covalent compound, we want to place the least electronegative element in the middle. Okay, and that's a correction from your notes. I think right now it says the most electronegative, but it should say the least electronegative element. So this is going to be the one that is furthest from fluorine. The only exception to this is hydrogen is never the central atom, just because we can only form one bond off of it because it's such a small atom. So that would be a pretty boring molecule if hydrogen was in the middle. We then want to try and make sure that we're keeping our molecule symmetrical. So we're going to place the other atoms around the center, again, trying to keep it symmetrical. So usually up and down, and then left and right. Next, we're going to place lone pairs of electrons on the outer atoms until they have an octet. Or we run out of electrons, whichever one happens first. Then we're going to check and see if we have any leftover electrons. If we do, we're going to place them as lone pairs on the central atom. And if we ran out of electrons at any point in time during steps 4 or 5, we need to check and see if we have an octet for everyone. If we do not, then we're going to change some of those lone pairs into either double or triple bonds to make sure that everyone has a full octet. Okay, so let's go ahead and work through some examples. The first one I want to do together is methane, which is the molecule CH4. Okay, so the first thing we need to do is find out the total number of valence electrons. Well, we have one carbon atom, and if we think about carbon, it is in group 14, which means that it's going to have 4 valence electrons. And then for hydrogen, I have 4 of those. I get that from the subscript. And I think about the valence electrons for hydrogen, which is 1. So if I go ahead and do my math here, 4 times 1 and 4 times 1, that gives me 8 electrons to work with. Now I need to figure out which atom will be my central atom, either the carbon or the hydrogens. Well, carbon is always going to win out over hydrogen because hydrogen can never be in the middle for a big molecule. The only time hydrogen would ever be in the middle is if it's just a 2-atom molecule, which this is not. Okay, so I put carbon in the middle. I then spread my hydrogen atoms around so they're nice and symmetrical. And I connect everyone with a single bond because I know they have to at least have a single bond. Well, now if I check, each of these lines represents 2 electrons. So I've used up 2, 4, 6, 8. So I have used up all of my electrons. So I'm really going to hope that everyone has what they want. Well, each of my hydrogens has access to that single line coming off of it. That means it has 2 valence electrons, which for hydrogen is good. Now, if I look at my carbon in the middle, okay, I have 4 lines coming off of it. So 2 times 4 is 8. So that is going to be the Lewis dot diagram for methane, CH4. Okay, so let's try another one. The next one is ammonia, which is NH3. Okay, so again, I want to start by finding out my total number of valence electrons. So I have 1 nitrogen. It is in group 15, so it has 5 valence electrons. Plus, I have 3 hydrogens. So that is going to give me a grand total, again, of 8 electrons to work with. Now, again, remember, hydrogen will not be in the middle. So I'm going to go ahead and draw my nitrogen, put that in the middle, and then I'm going to kind of just spread out my hydrogen so that I have a nice symmetrical molecule. Okay. So I've connected all my hydrogen with a single bond. Remember, everyone needs at least 1 bond connecting them to someone else. So if I look, I have used up 2, 4, 6 of my electrons, which means that I have 2 more left over. So normally first I would start by placing those extra electrons on my outer atoms. But in this case, my hydrogens already have their maximum number they're allowed to have. They have 2. So my hydrogens don't want anymore. So those 2 are then going to go onto my central atom, which is my nitrogen. So if I look at my nitrogen now, it has 6 electrons from the line. So 2, 4, 6, and then 7, 8. So it also has its octet. So that is my Lewis dot diagram of ammonia. Okay, let's try one more example. So the next one we're going to go ahead and do is carbon dioxide. Okay, so carbon, I have 1 of those. And again, carbon's in group 14, so 1 times 4. And then I have 2 oxygen atoms. And oxygen is in group 16, so 2 times 6. If I go ahead and add that all up, this time I have 16 electrons. So now I want to figure out my central atom. So I have a choice this time. The other ones I didn't really have a choice because hydrogen can't go in the middle. So I could put carbon or oxygen in the middle for this one. So I want to think about the least electronegative element, also known as the element furthest from carbon. Furthest from fluorine, which is going to be carbon. So I'm going to go ahead and put carbon in the middle, and I'm going to connect my oxygen with single lines. Now I'm going to stop and check. I have 2 4 electrons that I've used up, so I have 12 electrons remaining. And I'm going to start by putting those on my outermost atoms. So my oxygen. So 1, 2, 3, 4, 5, 6. And I want to put enough so I end up with an octet on each of my oxygen. So 2, 4, 6, 8. And then we do the same thing on the other side. So now I have used up 8, 10, 12 additional electrons. So if I look, I have now used up all of my electrons. I'm not allowed to add anymore. I can rearrange them, but I cannot add anymore. So if I look at my oxygens, they are satisfied because they have 2, 4, 6, 8 electrons, and again, 2, 4, 6, 8. But my carbon is not satisfied. It only has 4 electrons, 2 bonds. So I need to go ahead and change that. So I'm going to go ahead and take one of the lone pair electrons in an oxygen. I'm going to change it into a double bond. Okay. When I do that, I still have 8 electrons on that carbon. I now have 2, 4, 5, 6, 7, 8. So that is still good. And then for my carbon in the middle, I'm now closer to getting to that 8 because I have 2, 4, 6. So I'm closer, but I'm not quite there yet. So I'm going to do the same thing to the other side because remember, we want to keep things symmetrical when we're able to. So I'm going to add that line. Okay. Now, if you are using pencil, you can go ahead and erase those dots when you turn them into lines. Otherwise, make sure you clearly cross them out so you know what your diagram actually looks like and you're not counting them multiple times. So if we check, our oxygens are satisfied because they have 2, 4, 6, 8, and carbon is also satisfied because that's 2, 4, 6, 8. And if we check our total number of electrons, it should add up to 16. So we have 2, 4, 6, 8, 10, 12, 14, 16. So that is my Lewis dot diagram for carbon dioxide. So I hope that helps. You're going to have a lot more opportunities to practice this idea coming up. So please let me know if you have any questions. Bye.